AP style question number 2 is shown here. You're given concentrations at the beginning. Down here we're being told that the concentration of H2O is the same as the concentration of carbon monoxide, and they are both 0.55 moles per liter. So what is the mole fraction of carbon monoxide? Well, mole fraction is the number of moles of carbon monoxide divided by the total number of moles. So number of moles of carbon monoxide is going to be 0.55, and the total number of moles will be 0.2 plus 0.3 plus 0.5 twice, once for carbon monoxide and once for H2O. So this is actually a Greek letter chi. It looks like a big X, but it is a chi, and that's the symbol for mole fraction. Mole fraction of carbon monoxide. There's the moles of carbon monoxide, the moles of H2, of CO2, of H2O, and of carbon monoxide, because it's total moles. And we end up with 0.34. Next, you're asked to determine the value of Kc using these concentrations. Well, this should be very straightforward. You can tell from the balanced equation that everything is in a one-to-one relationship. So Kc is just going to be the products on the top and the reactants on the bottom. And we've got all these numbers to plug in. So everybody should get that the equilibrium constant is 5.04. Then we need to determine Kp in terms of Kc. I think this one was actually designed to separate people based on the time it took them to answer it, because the quickest solution is simply noticing that delta N is 0, therefore Kc equals Kp, which means that Kp is also 5.04. Now you can still do it the long way and you'll get the right answer. It just takes extra time, and if you don't have extra time during an exam, it's better to take care of quick points like this very fast and spend more time on harder questions. Then this system gets cooled down from 20,000 K, where we had equilibrium, to a lower temperature, and it's still going to reach equilibrium. But the value of K will be different because the temperature is different. So 30% of the CO gas is converted back to CO2. So 30% of this gets converted backwards into CO2. And the only way for it to do that is to also take some H2 with it and to also make some H2 as it makes the carbon dioxide gas. The 30% is used to calculate the number of moles of carbon monoxide, and then the number of moles of each of the remaining ones can be found. You cannot just take 30% of everything, because you should be able to see that 30% of 0.55 is a different number than 30% of 0.20. So 30% of 0.55 is 0.165 moles. And that means I can figure out each one of them by either subtracting or adding 0.165. It's also possible to use an ICE table for this, and you'll end up with the same result, because what really matters is this over here. What's the concentration? Once we know those numbers, then it becomes pretty easy to just plug them into the equilibrium expression, and we get our new K value. At this new temperature, K is 0.87, and the last one is in a different experiment. It is still the same equilibrium system. It's still 1 to 1 to 1 to 1. And this time, though, we get to equilibrium by putting in 0.5 of H2 and 0.5 moles of CO2. It's in a 3-liter vessel. and calculate the equilibrium concentration in moles per liter. Right now, we are back to the original temperature, and that's important. So this one here, very easy to set up an ice table. The 0.5 moles divided by 3 liters gives us molar concentrations of 0.167 for our reactants, and initially 0 for our products. Without knowing the exact number, we can state that for every one of the carbon dioxides that disappear, there is also one hydrogen gas that disappears, and there is one water and one carbon monoxide that appears. So I only need to figure out the equilibrium concentration in moles per liter of CO. So I need to get X. X is what I'm looking for. At equilibrium, my concentrations would be 0.167 minus X, X, and minus X. I should say X and X. So, like all examples given to you on the AP exam and given to you in the class, we can make the assumption that this difference, this minus X out of 0.167, is insignificant and can be ignored. So this whole thing simplifies down to x squared over 0.167x. And the whole thing has to equal 5.04. That's our K value. We calculated it before, and because we're in the same equation at the same temperature, it will be the same K value. So I only have one unknown, it's X. And when I solve for X, I find it is equal to 0.375. Now in the real world, we would notice that this number, 0.375, was a significantly different number than 0.167. So our estimate is not accurate, but we're going to keep practicing it this way because that's the way it will always be on the AP exam.